Hello, everybody, and welcome back to Modern Software Management. Modsoftman.com on the web, and the channel name at Modsoftman on YouTube. Today I want to talk about testing and my thoughts on, in particular, unit testing, which may be a little bit controversial. The first and probably most important type of tests are system tests. That's where you take, if your system is composed of many pieces, obviously lots of code that gets compiled together into big things, and then a number of these big things that may interact and talk to one another. So you need to assemble that entire system and test it as a whole before you can unleash it on anybody, obviously. There's no substitute for doing that. You absolutely must do that. It's absolutely mandatory to have that kind of testing. Now, that testing can and should be done with APIs. And if your product has APIs, then of course you test your production APIs, but there may be additional APIs that aren't productized that you might use solely for testing your own product. If your product has a command line interface, for instance, you might use that route. UI testing of the whole system, you're driving it as if a user was driving it, using something like Selenium, for instance, for web-based testing. Yes, you absolutely need to do that. You do also need to do manual testing. There's a saying that to err is human, to truly foul up takes a computer. So if you never have any human eyes on their next release, you can do things like have all of the text on a dialog box the same color as the background of the dialog box, and no one will ever notice that because it wasn't coded to look for that color contrast in Selenium, for instance. But like, first thing the user says, and if a customer gets it, they say, "Don't you guys even test this?" And of course you do. Now, so like I say, system tests, absolutely 100%, and an automated system test. You need a good suite of automated system tests prior to releasing anything, and you want to rerun those system tests on a regular basis as your developers are working. There's absolutely no controversy on that one. Closely related to the system tests are the production tests. Production tests, also, they kind of blend into the idea of monitoring as well, monitoring using synthetic transactions. So once you deploy your system, this is true for web-based systems especially, you then want to hit up the production instance with a continuous stream of synthetic transactions that basically test if everything still works. And state of the art is you have these red-green deployments, basically, where you deploy the new system to 10%, say, of the customer base, or initially 1%, and then maybe 10%, and you check these production tests and see if they're still coming back all green, and if they're still green, you roll it out to everybody else. And so that's, again, a very valuable kind of testing for that kind of system, and definitely it builds on your system tests, and you want more of that good stuff as well. And again, that could be done using both Selenium and API type stuff, and driven by monitoring systems. It also gives you the health of underlying components of the system. Integration tests are if you have a larger system and it's built using big components, for instance, things that run in containers, microservices that run in containers, and there's a bunch of these microservices that all talk to one another. Then what the integration tests do is they pull out either one of those containers or maybe a subset of those containers, and they use the APIs to test the generally internal APIs to test that thing and run it through its paces. And if you already have system tests running, and they're running regularly, super regularly, as often as possible, well, yeah, integration tests can still be useful. But they start blending into, what I'm about to talk about in unit tests. So maybe less useful. And finally, at the bottom are unit tests, where you're actually taking individual bits of code that you've written that are generally compiled into a larger system, and you're writing specific tests around that one piece of code to see if that one function or that one class is still behaving the way the developer of that class expected it to behave. And it's unit tests where I've got the big question mark. I started coding before unit tests And I've noticed a decrease in productivity over the years. And I think I'm attributing it to unit tests, although I'm not 100% sure. I haven't done any research I don't know for sure, but I'm suspicious of unit tests. Let's put it that way. And I know, oh no, that's heresy. I know it's heresy. Need to stress that I'm not talking about no testing, right? We're definitely testing. 100% system tests. Absolutely. Not no automated testing. We absolutely, well, I do think we need some manual testing. Absolutely, you need to pound it with automated tests as often as possible to catch bugs as early as possible. No question. So you need those system tests, automated system tests, regardless. But the question is, if you're already doing a great job on automated system testing, what's the incremental cost benefit of doing, I'd say, extensive unit tests? So here we have a cost benefit graph, right? Benefit here, cost along here. So say we're doing our automated system tests. You generally you're going to get a curve like this in the sense that, for a relatively low cost, you're going to achieve a really pretty decent benefit. It's going to be pretty steeply rising. And then the question is, once you've gotten to this point, can you get benefit beyond and at what cost? So assuming you put more and more and more effort into your system tests, you might get, it will definitely start flattening out, in the sense that the incremental benefit of doing a lot more is going to be smaller and smaller and smaller. All right, so that's where it stands. So how about unit tests? So say we, instead of going down this curve more and more, instead of that, we put in unit tests. And if the curve looks like this, well, it's definitely worth it. For a small amount of incremental cost, you get a huge benefit from unit tests. If the curve really looks like that, and if it looks like that, you don't have to go all the way to the end. You don't have to incur all this cost. You just add a relatively small amount of cost and you get a relatively big amount of benefit. And then you'll stop, say, at this point. Okay, what if the curve, though, looks like this for unit testing? It's worth it a bit. Probably better than doing system tests, as long as you're not spending too much time and effort on it. But if you have to spend a lot of effort on it, a lot of cost there for a very small amount of benefit, right? Or is it like this, in which case it's not worth it at all? Not worth it at all. So that's the question. So like I say, it's not a simple question of, oh no, you must do unit tests because you have to do automated testing. No, we're doing automated testing, doing a great job on automated testing. We're doing the stuff that has to be done anyways. Or is unit testing in particular going to bring you the extra benefit? Well, what does the internet have to say about it? I Googled it. Is unit testing worth the effort? My first result was a Stack Overflow page. And hey, I'm retired. I'll take the first result. That's good enough for me. The question is, hey, I'm working to integrate unit testing into the dev process on the team I work on, and there are some skeptics. What are some good ways to convince the skeptical developers of the value of unit testing? In my case, we would be adding unit tests as we add functionality or fix bugs. Unfortunately, our code base does not lend itself to easy testing. All right. This thing was shut down after a while. We expect answers to be supported by facts, references, or expertise, but this question will likely solicit debate, arguments, polling, or extended discussion. And it gives you a hint. It's a little political. It's one of these politically correct kind of issues. So let's say it says that has some historical significance, but it's not important anymore. This was 11 years ago. I think it still is important now. All right. Anyways. So let's see the first answer. Like what's the first answer here? How can you even ask such a thing? Unit testing is so hip. Seriously, the general idea is the same. Do unit testing if you feel that the benefits outweigh the cost. If you have reasons to believe otherwise, find something else that helps. Well, thank you, Gishu. That is that's an excellent answer. Here's someone, Victor, who says that, if you do a good job on coding, if you use lots of assertions in your code, if you do a good job on designing, and if you do system testing, I think is what he's getting at. That's better than doing unit testing. Okay, that's the point of view. This one, having been on a few teams with the same attitude, my experience is that you're wasting your time. The skeptics are just giving you the runaround and will sabotage and stonewall you until you're frustrated and move to an organization that shares your values, which is probably what you should do. If the quote unquote lead of the team is one of the skeptics, think seriously about getting out. I've seen this sort of resistance to unit testing as just the tip of the iceberg of bad development practices. I'm starting to feel like a Holocaust denier if I'm questioning unit testing, right? Oh, it gets religious. That's a religious answer. Dominic, unit testing is a massive waste of time that rarely ever discovers bugs and that eats away 30% of the bug fixing and development time and budget. Yeah, that's valid. These two would get into a great argument. I like that. It's fun. Are there more? Let's look at 5 more comments. If you're expecting to catch bugs with unit tests, I understand why you're disappointed. If you read the most upvoted answers, you will find that none of them states that this is why you do unit tests. It's not. You're not doing it to find bugs. If you're not seeing the other benefits, which he doesn't state, you're probably not doing it right. Okay, what are the other benefits that I've heard? It forces you to do a better, cleaner architectural design because you're designing it for test. Maybe. We could just do the clean design without all those unit tests. You're more free to change code because you know that it's still going to be correct if your unit tests still run. Yeah, you got system tests. The system tests already do that. They do a real good job of that as well. So I'm not exactly sure what the other benefits is. Here's someone who says it's a pain in the butt, but it's comforting knowing that the core functionality has been tested. It's comforting. Well, the system tests are more comforting for me. Like if all the unit tests pass and I didn't do system testing, I would not be comfortable. I would not be comfortable at all. Here's someone that looks at a paper written by Cope, he was a design patterns guy, and he worked, I think, with Grady Booch and Co. and around the rational type stuff, I believe. Why most unit testing is a waste. That's Cope's opinion. And there's a paper there that if you follow the link, it doesn't found. I went and found it using the Wayback Machine, so that's cool. That's what the internet says. When I started writing serious code, I was in university. I was doing my, I went through undergrad. I wrote a lot of assignments, obviously, honing my skills. When I got to grad school, I started writing some more serious bits of software that were used by a lot of people. I wrote an operating system called Mini-Tunis that was used for years and years and years in my university and others for teaching the principles of operating systems. So lots and lots of people actually used that, ripped the code apart and replaced bits of it and things like that over the years. So that was a big one. I wrote the object-oriented Turing integrated development environment with a team. So that was a new language called object-oriented Turing, and we wrote the IDE that had all the editors and the debuggers and the static analyzers. I did my PhD thesis in concepts around that, actually. And I also wrote this operating system called Pollux. So Pollux is was a 4.3 BSD compatible operating system at the kernel level. So it replicated all the Unix kernel calls. And we just compiled the usual cat and shell and ls and things like that. And they C code compiles, calls my system calls in the Pollux operating system as well. Didn't think a lot about testing. This was back in the from 85 to around early 90s, something like that. Automated testing wasn't so much of a thing. We would write code and we would test the code, and it's a university, so we didn't have a test team per se. We would just do our own manual testing and try to break it, maybe have a friend try to break it for you. And it was pretty high quality. Like something like OOT made its way, that integrated development environment made its way all around the world. I wrote the code that caught the one of the bits of code I wrote was the code that caught a segmentation fault, and I got into this little module that says, okay, we're in the process of dying. Something went horribly wrong. But there's these valuable edit buffers that poor student has been typing up their assignment for the last 3 hours and forgot to hit the save button. I'm going to try to do that for them. So using the smallest amount of code, accessing only the data structures I absolutely need to, checking pointer integrity before I did it, and using only raw system calls, I wrote out copies of all the files that were modified. And then I allowed it to crash. But I said, before I allow it to crash, I've got this core dump. Not a core dump. I've got a stack trace right here. I've got a nice stack trace. I'm going to package up the stack trace in an email message and attempt to email us back the fact that it dumped and the whole stack trace about where it was when it core dumped. That was early. That was like 87, late 80s, definitely. Not yet the 90s, I don't think. And the internet, that was before the internet, right? The internet was barely there, if there at all. And it was kind of, email was something that university people used, and other people used weird systems or no systems at all. So it was pretty cutting edge. And I remember when I put this code in, some of my colleagues said, you can't do that. You can't have it email people. It's a privacy concern. You can't just go and email. And so we compromised, and we put a disclaimer up when the program fired up that says, hey, you're getting this free of charge, but be aware that it sends us email if it crashes, and this is the information that's contained in that. And we deliberately omitted anything that would now be considered personally identifying information. So we did all that back in the 80s. That was fun. Anyways, but my whole point of that is it didn't crash a lot. There was one notable crash I recalled, and it was happening at our school as well as at other schools. And I couldn't figure it out. I knew exactly where it was dying, and I couldn't figure out how it got there. So in desperation, I went to our lab, our compute lab. That was a time when students would come into the labs and sit at the computers and type. And I stood behind them and I watched what they were doing. And there was a bunch of students who went to a button and they double clicked it. Because I don't know, I think maybe Max you double clicked or something like that. It was X11. You needed a single click on a button. That's it. It's like, no mom, don't double click it. No, this is the one that you single click. Anyways, they were double clicking the buttons. And as soon as I saw that, I knew why I was getting those crashes. It didn't happen every time you did it, but there was kind of a race condition set up when they double clicked that button, and I went back and fixed it right away. And that was the most notable bug there was in that thing. Anyways, I don't know if any kind of automated system testing or unit testing would necessarily have caught that. Anyways, so that was my early days. So not a lot of testing. I go to industry. I go to IBM initially, and IBM at that time had two cultures. There was the mainframe culture, which was very disciplined in the way they developed software, and they had a lot of testing, mainly manual testing. It was the mainframe culture. And we were on the AIX side, the Unix side, the cowboy hacker side. I know I had a colleague named Pat who came from the mainframe side and he wanted to make a change. He worked with us. He was an experienced guy from the mainframe compiler side. And he was shaking his head at us university cowboy hackers on this stuff. Because we kind of winged it. And but we had good results nonetheless. And some teams, and it's very different amongst different teams. And some teams did like a really good job, and other teams, my team in particular, we never shipped the thing. The project got canceled after it was finished, but before it shipped. I think I explained that before. Moved on to algorithmics, and algorithmics initially was a disaster area because of the history of how our app got created. There was a fairly big team that was building a trading application, and they were doing everything from the ground up. Like TCP/IP was considered some university hacker stuff. And so they were rewriting the network stack to make sure that the trades would happen in real time. And it's something that people did back then if they wanted high frequency trading type systems. But the company was late delivering anything that anyone could see. And so in desperation, the founder, CEO, went to a couple of the guys and asked them to just throw anything, like ignore the command hierarchy. You report to me now, put something up on the screen, work with this guy, put something that he wants to see up on the screen. And so they did. They did something in X11. They borrowed some of the code. They pulled it over. They used what they could of that code, which wasn't a lot. They put something up on the screen, and it was great. And the CEO was so impressed. He said, all of you guys, you now work for these guys. That didn't work out well. That was just before I joined. So all of the old team left. And that's when I hired one of those two guys, was a guy who had worked with me previously at the university and pulled me in as his manager. And I remember my first day was the last person of the previous team. It was his last day. And he was a guy I remembered from university. I had taught him at university. And so he knew me, and he came to me and he shook his head. He says, this is a very bad place. But I was young. I didn't care. I wanted a bit of adventure in my life. So I got a bit of adventure. All right. Anyways, the code was super buggy. And it wasn't the guy's fault. They did it. They worked miracles to even get it up on the screen. I remember when we did early demos, we threw up the X11 program window, and as you're mousing around it, it would crash. Oops. And it's embarrassing. Boom, big crash. So what I learned a trick from one of the financial engineers who demoed it. You put up one, and then you load the same data set and put up another one. Now you do all your edits on this one, all your changes and all your demos here. If it crashes, it doesn't crash to the blank screen. It crashes to the app. And it just looked like it just changed from this look to this mode. It's like, and they go, I don't know. I must have pushed the wrong button. And you keep going, and you don't repeat what you just did to crash the software. It was buggy. Eventually, so there were people who started testing that, obviously, and we eventually hired testers. Then we hired a manager of the testers, and they were doing a lot of manual testing against that. And when you have a professional testing group like that, and they do manual testing, they have what's called a test plan. And the test plan, it's a highfalutin term for a list of things I'm going to do, and the steps for each thing. What are the steps I'm going to do, and what do I expect to see as the result of those steps? So that's a test plan. And then you say, okay, we have to get through all of these tests and check them all off, and report back to the devs if there's any problems that you see along the line. So that was the test plan. So that went well for a while until we developed all these financial engineering functions. We had hundreds of them. And they were very fragile, because if someone changed something, it might break a different one because they're using common underlying code. And so we got a bad culture that we had to, basically a lot of the coders would pick up the code and clone it and then make some modifications to it because they were too afraid to refactor the code because they might break something that already works. And a client would get extraordinarily upset if that were to happen. So, but clone code is horrible, right? Because if you have a bug here, you fix it here, but that same bug was cloned 3 or 4 more times. So the bug persisted. And then the customer finds the bug in one place, reports that it's fixed, thank you. And they try a very closely related thing. And they say, you haven't fixed it. Oh no, we cloned the code. We didn't refactor the code. So that was bad. So I think I kind of did it. I wrote a little tester for it, an automated tester that would put a test framework around the thing, and that would drive it via APIs, and it would load data sets, and then it would drive what's called a simulation and get a result set and compare the result sets, do a diff, a kind of clever diff against an pre-established baseline, and it would just report. So we'd run that every day, and if it ever differed from the baseline, that would get reported. And then the way we established the baseline is initially we just threw in data sets and ran the simulations. We didn't care if the numbers were right or wrong. And then there was another team called the validation team that came along behind and validated that the numbers were actually what the numbers should be. So we had 2 metrics, total number of tests, how complete our coverage was, and then our validation metric, what percentage of those were validated by the validation team. And along the lines of you can't manage what you can't measure, you could measure this. And so it happened very quickly that we developed a great set of automated tests at Algo. What was especially cool about that was it was metadata driven. So coders would write classes off of certain base classes and then dynamically load them into the system to add these functions in. And then there was code in there that could enumerate through all of them and get the names of the things. And based on that, dynamically, we would find a matching directory and file that contains tests for that thing. So you only had to write that test framework once, and all sorts of stuff got added to it. And the whole point about that initial run, where we just generated whatever numbers came out, was there's these two levels of regression. You want to know it's at least the same, that it hasn't changed, that it doesn't change. It might be right or it might be wrong, but at least it's not changing. So if, say, 90% of the time it's right, then it stays right. But there's 10% of the time when you're just testing that you're continuing to be wrong. And occasionally that would happen. We would make a fix to something and it would break the test. And then we discovered, no, this is now the right number. So we just erase the old baseline and establish a new one. And again, this validation team came around and really made sure by using MATLAB and other things that it was truly accurate testing. So that was a really fun project. My next professional gig, I think, was Electronics Workbench. And I got there and we had, again, a manual test team. And I thought, oh, we can do better than that. So I wrote a big test rig in Perl, I think it was, that would put the system under test. One of the coders gave me some COM OLE. It was a Windows app. They gave me some COM OLE APIs that could fire up the app without showing the window on a screen. But the window was still kind of there. It just wasn't being shown. And then do certain selected things like load a data set, this was an electric circuit simulation, get the results and dump them back out again. So I remember I built this fairly complex thing. And I taught it once, the automated regression testing architecture. It was fun. This is the application under test. This was our app, and it had this OLE COM interface. I wrote a test driver, and it had plugins. So if you had different types of tests, each plugin, if it was load a data set, run a simulation, that was just one plugin, so we could have many, many tests that run by that one plugin, but then there are other things it could do as well. Then there was and this thing tended to crash when this thing crashed. So this thing would crash, this thing would notice, and it would crash. Or sometimes it would stay up. But COM and OLE was like really weird. They're kind of sharing memory. So this thing was compromised. So there was another thing called the test marshal that kept its eye on this process and made sure it was always up. It kept its eye on both these processes, basically, and made sure that they were always up. And if they went down, it knew from the results log where they were in the testing. So it would back up one test and do it again and see if that test is killed it, or was it the sequence of tests that ran up to that test and that test was the final straw that killed it, or was it that test that killed it? And then it would continue going like that. So we kept everything in our source code repository, all the baseline data sets and the baseline results, so that we could do the comparisons. And then there was a test service that this test marshal communicated to about where it is in the sequence of all the tests that needed to run, stored that in a relational database, wrote a Perl-based web server that served up in web browsers the results of the test. So you could both configure the tests, get the results of the tests, and trigger running of tests. A coder could do that from their own desktop, and they just point to a different test marshal, the one that's on their machine rather than the one on the central machine, something like that. So that was cool. That was a cool bit of software. I was very chuffed with that one. I think I gave this as an assignment when I was a university professor as well. It's a fun bit of code to write. So let's get back to unit tests. Let's see what it takes to write some unit tests. So in case some of you aren't familiar with that process of writing unit tests and what it evokes, and also I want to prove that I'm educated on unit testing. I know how to do unit testing. It's okay. I understand how to do unit testing. So let's start with, I did this a couple of episodes ago, how to hire a developer. I said, give them a trivial program that they write in front of your eyes, compute the standard deviation from a list of floating point numbers, input on standard in, and write the standard deviation to standard out. And this is basically the program, although I've translated it from C, which I did it there, into C#, Microsoft's Java-like language. And as you can see, it says it does console read line, so it reads the entire line. And if that's null or an empty line, that's it. You're done. Those are all the numbers you're going to get, and you go ahead and compute the mean and the variance and the standard deviation from the sum of the numbers, the number of numbers, and the sum of the squares of the numbers in this way, and you write that out. If you do have a line that's non-blank and non-null, you try to parse it into a single precision floating point number x. And if for any reason that doesn't work, that's it, you're done. So you can type like 1, 2, 3, and then the letter A, and you're done at the A. It's not an error, but the 1, 2, 3 is the input at that point. So that's basically how that program worked. So, okay, so if we want to unit test this, first of all, I mean, you have to question your sanity if you want to unit test this code, because you can kind of tell by inspection it's correct. But if I was in a company and it had a corporate policy that I must put in unit tests and I must have 80% coverage of all new code, I'd have to write unit tests on this thing. But anyways, whether it's sensible or not, the types of unit tests I write is going to be very typical, and it's going to illustrate a bunch of things. So let's kind of get into it. How would I do that? So the first obvious thing to do is there's this logic involving n sum x squared, and these summations here, and then the computation of the standard. Can I factor that out of everything else it's doing, put that into its own routine so I can test that? So let's see. So what we need is this kind of routine, an SD routine where you give it a list of floating point numbers, and it will return the floating point standard deviation as the result. So I want to kind of move some of this code in here. So in true called TDD fashion, TDD stands for test-driven development. Test-driven development, you write your tests first and have them fail, and then you go and you fix your code so the tests pass. It's a style of doing unit testing. You can either do it like that, or you can write all your code and then write the unit tests later. One or the other. There's advocates of both approaches. I cover both of those when I'm talking about unit testing. So here would be your new main code driver. You'd write out the standard deviation of a list of floats. So I'm using C#'s enumerable generic. So it's an I enumerable of float is the parameter. When I previously said list of floats, I've translated that into the I enumerable of float. So I stands for interface. So it implements an interface. C# doesn't have multiple inheritance, but you can inherit from one base class and then implement a lot of interfaces, which is like a kind of inheritance that doesn't get you into the same kind of trouble that multiple inheritances does in C++, for instance. But anyways, and an enumerable is any kind of data structure that you can go from beginning to end through. You can enumerate through. So some kind of a list. So it could be an array, or it could be a linked list, or all sorts of other data structures. That's my prototype for it, and this is how I would call it. This is a C# syntax for creating an array of floats containing the numbers 1, 2, 3. All right, so I can go ahead and I can run that, hit the run button, and it immediately hits the not implemented exception. That's what it should have done, right? So, but that's not good. I don't want to do that. I want to add unit tests. So I go into my solution and I add in a new project. And the new project is the NUnit test project. And I say next on that one. And it, in addition to my standard deviation, this is where my program is in that program.cs. It's added a second project called the test project as well. And it's automatically written for me the first class called tests and the first test called test1. And it's a trivial test. It just passes. That's all it does. There's also a setup. Setup is called immediately before every test that it calls as well. So then what you do is you go up here and you say, okay, let's run all the tests. And it goes ahead and it does that. And you have your test explorer pop up. And it says, yeah, there's one test in the project. And there's one test in the whole solution. There's one test in this project. There's this one class called tests. And there's one test in there. And then there's a test called test1. And that one passed in 68 milliseconds, which is a ridiculously long amount of time. But don't worry, there's startup overhead. Great. So now what you want to do is you want to add a project reference into your test project. And you select your program that you want to test. And then that adds it in as a dependency to your test project. So now I can call things that were exposed as public interfaces in program.cs. So now I can actually write my test here. So I say, okay, assert in this test is going to assert that it's true that when I run my SDev program's SDev routine on this array, a floating point array of 3 numbers, 1, 2, 3, that the result is that. And I use precisely equal because I've expressed my answer in more precision than a single precision floating point number. So it will automatically round this to do the comparison down to a floating point, a single precision floating point, and it should be exactly equal. Then I can go ahead and run that. And of course, it's still going to fail, right? Because I still haven't implemented it. But in true test-driven design fashion, I'm going to add in a whole bunch of other tests. Okay, when all of the numbers are the same, it should be 0. When there's only one number, which is 0, it should be 0. When I put in really big numbers, I should get the big number, the same result here, but raised to the power of 23 times 10 to the 23. And when I give it an array that contains nothing, I'm expecting a NaN, a not a number response. So I'm just testing if the float I'm getting back is indeed the not a number float. So that's my kind of my definition of the behavior of this routine. And you could obviously write a lot more tests than that on this routine. Yeah, diminishing returns, absolutely. So I fill in the implementation. I'm now getting my IEnumerable of floats. And I use this for each loop. This is, if something is an IEnumerable, there's a built-in language feature in C# where you can use the for each loop, and you can use this syntax. For each x, you're declaring a new x inside of the scope of the for each, a floating point number x. For each x in this enumerable, which happens to be an array, but it could have been a linked list or it could have been many other things. I'm going to go through each one of them until there are no more, and I'm going to sum the squares and then do my computations and then return that. I can then go ahead and run my tests again. And what do you know, but my tests now pass. Fantastic. And that was like all 6 of them that I wrote passed. That's great. And I can also go ahead and now run my main program that does this. And sure enough, it prints out the answer that's expected on the console. And so going back to the original program, right? This is back to the original program that I had. Notice that I'm reading lines one at a time, and then I'm parsing the lines one at a time. So I can actually take out the parser and write a test around that. So here's my new prototype, parse floats from lines. I'm going to pass in a list of lines. And I'm going to pass back a list of floats. And again, TDD, I haven't implemented it yet. And I'll change my main to make it compilable. I'll pass into SDev the list of floats that comes back from parse floats from lines. And this time the test is strings, string 1, string 2, string 3. Right? And SDev is now unchanged on that basis. So now I can go back into my unit test code over here, unit test.cs, and I can write a bunch of tests. So I wrote a little helper function called isSame. IsSame takes lines in and is given the expected floating point answers. So it calls parse floats from lines of those lines, gets back a sequence of floats, and then I use the built-in sequence equal. Is that sequence equal to this other sequence of the expected values? So that'll return true or false. So then I assert that it's true, that it's the same. The strings 1, 2, 3 passes back the floats 1, 2, 3, and so on and so forth. And I do some corner case tests as well. Like if it's empty, I make sure I get back an empty list. If it's a big number, I make sure I get back a big number. If I have a list that ends with like the character A, I get just a list that ends just after the 1, right? It's only a 1 element list. And this one is an interesting one. If I put in like 2 numbers on the same line, it tries to parse that entire line as one floating point number, and having a space in there is a syntax error. So that fails, the try parse fails, and I get back therefore an empty list. And that actually is the correct behavior. You can quibble if that is the way my program should work, but it does work that way, so whatever. So now let's go in and implement it. It's really easy. For each of the lines, I again use the for each statement. I try to parse it, right? I try to parse that line, the next line in lines, and I put it into the parameter x that I'm declaring in line here, out float x. Out means it's coming back from this routine, and I'm declaring it here. And if it doesn't work, I just break, and that's the end. If it does work, I yield return x. Yield return x. What that yield return? It's a very cool and very useful C# language and library kind of combo a feature. Let me just explain it a little bit because it's interesting. So I wrote a trivial program. I wrote a routine called first 5 numbers that returns a list of integers, and the list is 0, 1, 2, 3, 4. It just does a bunch of yield returns, and then it finally ends, and that's the end of the list. And so this is how I use it. I say, well, the thing that this function returns is an enumerable, so I'll stash it into numbers. On numbers, I can get an enumerator, which is like an iterator through the list, and I'll call that the enumerator. And then on the enumerator, it's an object. I can move to the next number, which at the beginning moves to the first number. And then I can write out the current number, and then move to the next number, write out the current number, and this returns false when there are no more numbers, and then it ends that way, like that. Or more concisely, I can use that for each statement that I showed you before. I get back the first 5 numbers. So for each int I in numbers, write the line. I could have just said first 5 numbers directly in line there as well to be even more concise. And if you run it, sure enough, you get a 0, 1, 2, 3, 4 as your output. One of the reasons this was done is a C# feature called link, language integrated query. Say I just wanted to print out the even numbers. Well, you can write what's called a link query from your numbers enumerable. So you say from E in numbers, where E, the element mod 2 is 0. So if it's an even number, select that. And so that basically modifies the query to only include the even numbers. And then you can iterate through the link query as if it's an enumerable. It is an enumerable. And you can write it out. And when you run it, you get 0, 2, 4, which is freaking cool. And the important thing about this is that at no point are you actually making a list of numbers. You're not like allocating a big memory array and stuffing it with numbers, and then allocating another memory array and stuffing it with even numbers, and then running through that second array. You're nowhere using storage in this whatsoever. It's coroutines. The coroutines bounce back. When it needs the next number, it goes and calls first 5 numbers again, going back where it left off. So if it had already returned 0, and then 1, and then 2, and then it comes back the next time for the get next, it'll start after this statement here and return 3. That's the way it works. So nothing is ever stored. So it's a very cool language feature. But why you might say. Went to Substack again, and here's someone who's saying, hey, I've created a linked list in Java using Java generics, and now I want to be able to iterate over with all the elements. In C#, I just use yield return. But how do I do it in Java? And somebody suggested, yes, the first person suggests, oh, you can do it. You just it's a bit wordier. You can write this and do this, and you can kind of get more or less the same thing. And then here's someone actually has a very good answer. Yield return is a very sophisticated compiler trick. It basically lets you declaratively implement IEnumeral without any of the annoying details of figuring out how to build your iterator. So the only unfortunate thing is that it's a C# compiler thing, so it's hard to do it in other languages. So if you get used to using yield return in C#, that's not good for any other language. You won't see it. So it's revolutionary and damning. And it basically goes on to tell you what the compiler is doing under the covers. And he says, okay, here's an example of how useful it is. Say you wanted to write something that concatenated two numbers together. So you might want to write this concat function. Over here, it takes in a list where the elements are type T, called X, and a similar list Y. And so you just basically run through all of them and return all the ones in the first list, and then return all the ones in the second list with yield returns, and you're done. That's your whole program. And then he coded the same thing in Java. So that's, okay, here's the same concat function in Java. Yeah, okay. Oh, got to create iterators. Ooh, they have certain routines you have to fill in. Oh, okay, yeah, a lot of code. Oh, no, a crazy amount of code. Oh, no, that's, oh, look at all the code. Oh, no, too much code. Oh, and it's all useless code. Oh, no, there's even more code. Ta-da. Anyways. Yeah. So it's a cool feature. That's why. That's why it's in the language. Okay, so what's next is the question. So going back to the original program, remember we already factored out all the standard deviation stuff. Now we factored out the thing that parses line. So the only thing left to factor out is the thing that read lines, right? So we'll work on that next. So we'll create another routine called read lines. It'll also return an enumerable, an IEnumerable of strings. And basically it does the same code that you saw before. It does console.readline into the next line. If that's null or empty, return, exit the loop. Otherwise, do another yield return. So again, I'm using yield return here. This odd declaration of next line with the question mark, that declares what's called a nullable. So next line, if I didn't have the question mark after the string, next line is not allowed to have a null value assigned to it. And the trouble is console.readline can return a null value. So that's the type of it, is a nullable string. So you have to declare that or the compiler will get upset at you. And so then if I rewrite my main driver, like read the lines, get a list of strings, insert that list of strings into parse floats from lines, get back a list of floats, send that list of floats to standard deviation, get back the standard deviation, write out the standard deviation. So 1, 2, 3, Control Z, I think is Windows end of file character. And it prints out, the 1, 2, 3, the standard deviation again. So I got my program back to working again. So this is my program in a nutshell. I've just elided these three functions. Standard deviation, which it takes a list of floats. Parse floats from lines, gives it that list of floats from a list of lines. And read lines produces the list of lines that appeared on the console input. And then we look at our unit tests. And again, I've elided them. I basically have a first test here that tests the standard deviation function, a second test that tests parse floats from lines test. So I've got two of my routines tested, right? I've got parse floats from lines and I got tested. I don't really need to test read lines, do I? Well, if I want my code coverage up, I really should. But doing read lines is a little problematic because read lines has this console.readline, which is kind of a global variable. And the only way I could test read lines is by somehow injecting behind the scenes stuff into standard input and doing that over and over again. And I don't know, that's tricky. A lot of code. I don't exactly know how to do that. And again, it would be probably insane, completely insane to write a unit test for these 3 lines that are obviously correct, right? But hey, we're doing unit testing and we want to get that coverage up. And I'm going to illustrate another important principle of unit testing, which is dependency injection. If it depends on console.readline, instead of just depending on it, you inject it in. And so the way you inject it in is you pass it a function that takes no parameters and returns back a nullable string. So that's a pointer to a function that you're expecting here. You pass into the read lines. You don't tell it to read a line. You would need brackets at the end of read line if you want it to read a line. You're passing it the function read line, a pointer to the function read line. And that goes into this reader parameter. And then down here, I call whatever function was passed in at this point. And so now I've done dependency injection on my read lines. So I've decoupled read lines from console.readline. Now I can read lines from anywhere. Is that useful? Okay, yeah, I don't know. Now I can write a test. I have some test lines. So I just wrote one trivial unit test. I have some test array of lines and a pointer into it, the next line. What's the next line in the array? 0th line, first line, second line. And in my setup call, I reinitialize next line to 0, so I can use it over and over again. And I implement a private function to this test class, which is called readNextLines function. And it takes void and returns nullable string. And it basically says, if I've reached the end of the array, return null. Otherwise, index into the test lines array, the next line, and then auto increment next line after that. So every time this is called, it marches through 1, 2, 3, and then returns null. So then I can write a test for read lines called the readline test. And I can assert true that if I pass it read next lines, this function as a parameter, that the lines I get back is a sequence that exactly equals the test lines I gave it. Hooray. That's true. Wow. I'm impressed with myself. We'll run all the tests again. And you can see we get back the results. It's now running the standard deviation tests. Those ran. The read lines tests. Those ran. And the parse floats from line tests. It ran and they all succeeded. So I'm kind of done. So there's my original code. 20 lines. That's how big it is. Same font size. Here's my fully unit tested code. My code blew up to double the size, 42 lines. But is it a better architecture? Yeah, certainly is more complicated. The dependency injection is crazy. Maybe. And I have to write more lines of tests than I did of code. So the whole thing is 4.3 times bigger than the original code. That's a lot of code to write. It's a lot of code to write. So I better get a lot of benefit, right? If I'm going to write so much extra code. And remember, in this little thing, according to my thinking, you would have had a system test anyways. So you'd have had a test driver outside of this thing that would run, that had a bunch of files with a whole bunch of inputs and files with the expected outputs. And you'd run them through all of them, one after another, and test every possible case of your code. And so I'm saying absolutely you should have that. So given that I have that, how much extra benefit is there from the unit tests? None, I would argue. And as a matter of fact, the code got there's more of it and it's more complicated. This code was fine. This code is overly complicated. It's neat. Oh, it's neat. And it has dependency injection. It's unit testable, but it's more complicated. And there's just more things that can break. And it's just bulkier and everything around it. So you might argue, okay, well, Dave, it's a trivial example. If we're writing a really big system, then we'll want every little part of that system. And every little part of that system, while it's true, every little part of the system is as trivial as your little thing here. For some reason, I'm, multiplying it by a factor of 4 is going to be good when I add them all up together and the whole thing is multiplied by a factor of 4. But in your little example, it's not good. But in a big system, it is good. Even though you have complete system testing, integration tests where you need it. Unit tests on like key algorithms. Yeah, fine. But no, we got to put it everywhere. Absolutely everywhere. And we wonder why coders are less productive now than they used to be. I wonder. You be the judge. Was it worth it? For a small amount of extra cost, did we get this huge incremental benefit of cleaner code and more correct code and code that you can change? Given we have system tests, right? Given we have a complete suite of system tests. Were we on this line? Were we on this line? We were on this line? I think we were on a different line. I think we were on a line that increased the cost and decreased the quality. I think we're on this line. Honestly, I think we're on this line. Well, here was that paper. Cope agrees with me. The cure is worse than the disease. Yep. He relates consulting customers, and he relates one of them who says he joined a new team. The original team all left. They had a lot of complex unit tests. My new team, which is more experienced, said these tests are like a dog's breakfast nightmare. And the guy says, what do I do, Cope? I think Cope would say, throw out all the unit tests, right? Tests for their own sake. He says, yeah, I've been in places where we've had code coverage metrics, every new line of code, every new piece of code should have at least 80% coverage by your unit tests. That's something to aspire to. Yeah, maybe. The belief that tests are smarter than code. This tacit belief amongst programmers that they can think more clearly or somehow guess the architecture better when writing tests than when writing the code. Like, why? No, I can think clearly. If I wanted that fancy architecture for standard deviation, I could have done that fancy architecture for standard deviation without writing tests. I didn't need the tests to write that. I could have just been thinking about, if I did want to test, this is how I would do it, but I'm not actually going to write the tests because there are ways. But or not, I can just say, well, this is how you structure it correctly. I don't know. Low risk tests have low and potentially negative payoff. What he means by low risk tests are tests kind of like that test of my read lines function. Yeah, it's only 2 lines. It's never going to fail. Don't write a test for it. Because he says, you're going to get back a string of ones. Pass. It will never fail. And he's conjuring up some Shannon information theory that says, if you have, how much information is in a string of ones, an infinite string of ones? And the answer is 0. It's the log of the number of different states. There's one state, log of 1 is 0. So there's 0 information in that test. It just bulks up your code. You pay for tests in maintenance and quality. Yeah, there's just more code. And yeah, did your design really get better or did it not get better? I would argue that my standard deviation, especially with that dependency injection, got worse. Yeah, like I say, more elegant, but harder to read. You have to jump around between all the things. I had to go to some trouble. I think the first one was easier to read, honestly. So he wraps up with some recommendations here. He says, throw out regression tests. If they haven't failed in a year, you don't need them. Well, that's radical, actually. Keep unit tests that test key algorithms. So if there's like a complex algorithm somewhere, he's saying, yeah, no, a unit test for that. Be sensible. That's good. But don't do it for everything. He says, if you can test something that has business value in either a system test or a unit test, do it in the system test. That's more valuable. You have to do it there. Unit test, don't bother. He says, turn most unit tests into assertions. You can assertions is a style of programming where you assert things are true throughout your live execution. You can take those out at runtime or not, leave them in. I'll talk about that at some future point. Testing can't replace good development. I think he says here, be humble about what tests can achieve. Tests don't improve quality, right? Developers improve quality. Tests just point out where the developers screwed up. It's the developers who are putting in the quality in the first place. When I hanker back to when I was writing code, I was like super coder and writing a lot of code. And the code, it was really pretty correct. I didn't make a lot of errors. And I agree, you need testing, you need testing, and you need system testing, and you need automated system testing. It's like really valuable because if you want to refactor code and you don't have a comprehensive suite of system tests that will run like the minute you make that change, it's really risky making big changes like that. So you really want that safety harness of you make a change in some complex code, you run the tests in your own private repo still. If everything all works, yeah, great, you can merge it in because you know it was subtle code, but you're confident that the subtle code works. So you need system tests, and you need really good system tests. But do you need unit tests? I don't know. Anyways, thank you very much for your attention. Please remember to subscribe and hit the bell to be notified and the like button. And I'll see you all next time.